with some trace formula. Trace formula is some, okay, what I like to have in mind is a very simple fact that if you consider matrix, and if you, as you learned in the course of linear algebra, it is defined in this as an sum of the diagonal entries, but also we can define, or we can show that this is the sum of eigenvalues. So this is eigenvalues of eigenvalue of x1. And okay, but we like to see this kind of thing in more general setting. And what we consider is LT. This is transfer operator. And this is also operator which is the action, push forward action on function. So ft minus tx. Okay, this is a push forward action of flow on functions. And okay, then we write it in the following form. So this is a Dirac function, and y minus tx and dy. Okay, it's simple because if you consider integration, but this takes value at y for f minus tx, so just put it and we get this one. But the good thing for this is that we can consider it as a matrix like xy. Okay. So we can consider trace in this way. So this is a trace called flat trace or Archibald trace. So LT. We define it in this way. So just we take okay, instead of sum we take the integration of this dx and dx. Okay. And we will find that this is we can complete this because okay, at least we can this takes value, non-zero value only as a point of periodic point. So if you have periodic point of t, then you have some value, but otherwise you don't. And so, and also you realize that actually this is not a very smooth object in t, because if you take each point t, then it takes value 0, because in most of the case t is not a period of some periodic object. So actually most of the point t it takes value 0, and at some point it takes some value infinite. So what we can imagine is that trace of this L t is some function that we can write like this. So this is a period of periodic object. And there are some other. So this is not a function. It's a distribution in t, and but still we can compute it. And this is can you see this or no?
I think also bottle.
The bottom line.
Bottle. Okay.
And yeah,
Then okay.
Bottom line.
that's a, don't go for it.
No, okay. Then, this is actually not a complicated formula, so I don't like it to write it. And so what we have is that it takes value only in this place, so minus n, and okay, gamma is a prime periodic orbit, and okay, then we put a multiple n, and other place than that, this okay, the value of this place is 0, and here we have some weight, and this is okay, determinant of minus d gamma n. D gamma is a transversal Jacobian. So if you have a periodic orbit, okay, like this, then you take a Poincare section, then you consider the derivative the gamma, then you get this matrix. Okay. So it's an interesting formula. Okay, unfortunately it is divided into two, but okay, trace is computed in this way. And it contains some information on the periodic orbit. And okay, suppose that if you have well, this operator LT have a very nice property, like okay, if generator have a discrete spectrum, then what we expect is that okay, this is not so okay, this side. Okay, this is just expectation, but okay, if you know the spectrum generator of this, then we expect that if this is my something like lambda IT, okay, IO, okay, 0, 1, 2, 4, okay. So basically, the distribution of weighted distribution of periodic orbit is governed by the spectrum of generator of this class operator. And actually, I don't like to have this factor. And to erase it, we invent some technique. So let us extend it to the case of differential form. So let us consider omega k perpendicular. This is k form. So k form is C into n and p star n and which vanishes in the four direction. So let us say that x is a generating vector field of f. Then we take inner product. Then this is 0. Okay. We consider this kind of k form, differential k form, and action. We consider the action. Then we again do computation like this. But now we have this, in each point we have some fiber and action of flow on it. So we have something a little bit different. And let me just write it. Maybe if you like, you can just compute it and get it. So place of L A T equal okay, some singular sum and and then this sorry, I forgot one. This is sorry, and place of d gamma n sum of this factor. Because so actually we have some formula like this. So determinant of identity minus A equals sum of A equals A to B and trace of A to the K times 1. And if you compare this, so if you use this then we have, so we take alternative sum like this, and A equals 0 to E. Then we have this factor, if you take alternative sum, simplifies. So gamma and that minus gamma, and the weight is just period gamma. And maybe we have this, actually we have this. Sorry, I forget to write this. And so actually we and also since sign depend on the image of unstable marker. So actually I like to transform it. But anyway, we have this simple formula. So okay, let me start again from here. Um, okay, therefore, if you consider, okay, let me call it classical zeta function. This is something like what we consider 1 minus e to the minus s gamma. And gamma is a prime period. Okay. And as before, actually, we can write it in the following way. So exponential of minus sigma gamma n over e minus s and gamma. And with this formula, okay, we can write it. Sorry, and then we can minus k equals 0 to minus 1 and this time minus e raise of k. So again we have, so we could use this here, then we can write it in this way. And this is a basic format when we consider the analytic property of this zeta function. Because if you know that, again, if you know that this is, we know that the generator of this class operator is discrete, then we can expect that this function is meromorphic. And and this is indeed done by recent work of Giulietti and Riverani and Poitot. And also Jacob and Zworsky, that this function, so zeta function, has meromorphic sum. Extension. And okay, singularity corresponds to eigenvalue, discrete eigenvalue of generator of LKT. So what actually they prove is that, okay, first this LKT have act on some good function space, the completion of some space, the space of space, in a nice way, and have this each generator have discrete spectrum, and then they relate use this, and okay, yes,
Singularity is either 0 or 4.
yes, yes.
And you mean possible singularity.
Sorry.
You do not claim that there will be singularities at all with eigenvalues. There could be cancellation.
Ah, yeah, yes, yes,
Right?
yes,
Yeah.
yeah. So if you count things in with multiplicity, then the correspondence is 1 to 1. But okay, sometimes they cancel each other and automatically 0. Yes. Okay. So actually, this is the point that I want to address. So this is a nice expression, but this is not a homological one. So this is just a formula in the quotient level. But we expect that there are some cancellation, because if we take some with this, we are taking alternative sum. So what we have is that each level we have an operator like LT0 and L1, L1T. Okay, but I want to ask the relation between this. So, because we are considering space of differential form, so a good idea, seemingly good idea, is to consider exterior derivative. Okay, let us consider. But the problem is that if you like to consider differential operator, exterior derivative operator, then okay, this space is not preserved. So we got in the problem. Firstly, this is not not defined. Okay, so the problem is that so we have argument on the quotient level, but we cannot go into the cohomological level. So actually, I come back to this problem very often, but this problem is very interesting, I think, and but the problem is too interesting, so I have no result. So let me move to a little simpler case. This is a good variables data function. Okay, so good variables. Yeah, yeah,
Where?
yeah.
That's dangerous.
In sorry,
Dangerous.
Oh, yes. Okay, but they have definitions, so I can do some mathematics.
Good
Uh,
Vita.
Good.
Good Vita. Vita.
V, right? Yeah. V. So they are physicists, and what they consider is what I like to consider semi-classical data function. So in this case, the definition is a bit more complicated. But what I like to claim is that this zeta functions actually have very nice property. And 1 over n e to the minus s n gamma. And we have some strange factor like this. Minus e gamma n. And we take square root. This is quite strange. Okay, maybe we first have to then okay, one.
I'm confused. Do you have a
Yes.
general definition of zeta function so that any of those you show here is an example of that general definition?
Yeah, yes, there are many. But what I
one which would cover everything.
you mean that you consider some cocycle and then define the some.
That's the zeta function.
Yes.
And then because
Yes, but this is the point that I want to discuss. So, but some zeta function have nice property, and the others not.
but I mean
Yes.
if there are different zeta functions, why are they all called zeta functions?
Sorry.
If there are different zeta functions, why do you call them all zeta functions?
I don't know.
Well, that's what
Okay, we can
I'm
discuss.
going to explain why the square root in fact helps.
Yeah. So actually, if you consider some quantum mechanical thinking, so what they did is that they consider some Schrödinger evolution equation. Okay, and Schrödinger semigroup, and they compute some kernel by some double KB approximation, and we consider its trace. It's somewhat for mathematicians it's rather crazy, but they did compute it. And then what they expect is that actually this function will have zeros at the square root of eigenvalue of Laplace. So its zero should be their conjecture, not mathematical, but their conjecture is that if the zero of this should be connected with Laplace, that of Laplacian, in the case of Jodhpur. This is what they consider. And this is and they express this. I cannot go further in this explanation, but okay, let him proceed because this is mathematics and we can define it. So, and in the beginning, this is very strange object. You see, we have square root. I don't know, at least from this thinking of classical mechanics, I have no reason, I don't find any reason to take this square root that they take. And okay, we'd like to consider two homological derivatives. The first we again develop Cochain level argument. So in this case, we consider as differential form, but restricted to unstable manifold or unstable correlation. So EU star to K, wait for K. And unfortunately we have to take some, so EU, but this is a determinant bundle of EU. And we take this is strange, but okay, for the moment let us accept it. Okay, so we consider then we have very natural action of flow on it, and then okay, it induces action on the section.
You have a natural action of what?
Of flow, because EU moved to EU, so it induces mapping on the operator on section. Then okay, we do similar computation as before. Then we have nice formula in the Cochain level, so theta SC. S is exponential of minus 0 B. I'm sorry for this rather complicated formula, but I think this is rather simple. So B minus 1. Okay, maybe for this we need to do some computation, but quite the computation itself is quite informal. But now I want to emphasize that okay, we at this moment this expression and this expression is parallel. But what makes the difference is that we have deduction to homological space. Because okay, let us write this and gamma 0. And okay, so we have gamma mapping or transfer operator in 0 level and 1 level. Okay, and 2. And we can consider the exterior derivative along unstable manifolds. So let us write it d u and maybe level 0, so 0, d 1 u, and so on. The point is that so EU is integrative. So we can consider the exterior derivative like this. Okay. And the point is that it gives some cancellation between zeros that is obtained by the spectrum. Because, for example, if you generator of this have one eigenvalue and its eigenfunction is mapped to d0 u here and it does not vanish, then actually we have same eigenvalue here and here. And since we take this alternative sum, it cancels each other. And what is left is that in the homological space. So this is what I did recently. So let me write it. So theorem A. Okay. So we can define some Hilbert space. So in order to do some functional analysis, we have to how I do it? This is K equal okay, this space. So let us write. So this is not gamma K. This space, and this is a closure or completion of this space with respect to some metric, some node or inner product. Let me say such that actually so we consider completion of this space, these spaces, and so that this operator lambda k to lambda k plus 1 and also LT k, this is lambda k to lambda k, is bounded. So first, so if you put, so this becomes a diagram of Hilbert space and the bounded And second, a generator of LKP as discrete spectrum. Actually, I'm doing a little. This is not very precise because actually we cannot observe this discrete spectrum at all times. So what we can do is that okay, we fix some C and C, and then we can observe that this has discrete spectrum on the right of this half plane. So actually, this statement depends on some constant. So for any C 0, then discrete spectrum on real part of S and minus C. I'm very happy to obtain this because okay, this data function which looks something kind of strange in the beginning, but it accepts some nice homological interpretation. And also, okay, I have not picked the homework for this. Okay, this is in this preference of mine, but I can say that if okay, actually homological space other than the bottom level is almost vanishing. So I can't show that it's vanished completely, but basically what I can show is that this is compact for T. It implies that actually this does not have many eigenvalues. Okay. Yes, I can have 5 minutes more. So this result, maybe this is not a result, but okay, kind of complete. But I'm rather sure that this is.
Sorry, I don't understand.
Yeah.
If it's compact, then it has a discrete spectrum, right?
Yes. So if you fix T, so positive T, then yeah. So if you consider the generator, then
Okay.
okay.
Yeah.
Actually, if we combine it with my recent result with Frederick Forer, actually, I wrote the paper long ago, but published last year. It is rather interesting because, okay, first, so let us discuss. So, this FT is geodesic flow on hyperbolic surface. Then, this semi-classical zeta function, or Gutzwiller zeta function, is actually Silberg zeta function. Plus 1 half. There's some shift, but it's not important. So, actually, in this case, what is known about this? The zero and the full, this is zero of this zeta function. And it is known that there are countably many zeros on the imaginary axis, and there's some zeros called trivial zeros on the real line. And basically, this zeros is correspond to eigenvalue of, okay, this should be like this, of the Laplace. Okay. And what we observe in the case of FT is contact tensor flow. If you like, you consider just a variable current case. Then, what we did in the previous paper is that actually this this description actually continues. So what we observed is that there exists a convergence we observe convergence of 0 along the imaginary axis, and there is some space on the right, on the left, and here we don't know. But okay, on the outside neighborhood of this imaginary axis, so this neighborhood becomes smaller and smaller if you go to infinity. And then there are only finitely many exceptional eigenvalues, zeros of zeta ST. So basically the result of Selbach remains true or deformed into the case of a contact constant like this. And what we can say in this from this is that actually that these eigenvalues corresponding to the zero eigenvalues of generator of L0k, L0k, because basically for k bigger than 0, we have basically finitely many eigenvalues here. So the rest should come from this one. And what is this operator? This is an okay, this one, but k is equal to 0, right? So we just forget about this. We have this, but this is just a line value. So okay, it is not very good, but okay, let's forget it. Then after this action k equals 0 is just an action of flow on the function or distribution that is constant along the unstable manifold. So okay, so this eigenvalue comes from that kind of action. So if you consider answer flow and you consider some distribution which is constant along the unstable manifold, and we consider that kind of space. Maybe if you just consider continuous function, then maybe you only have constant function because maybe unstable manifold exists. But if you consider distribution, it's not the case. And you consider the action of flow on it, then you will find this eigenvalue. And very curious for me is that long ago people considered something called geometric quantization of flow, Hamilton flow. And if you take, and in that case they consider something similar to this, and then they say that we consider some foliation, what they call polarization, and they just want to consider function which is constant along that foliation. So in this case, actually, we take as very natural foliation for us. This is unstable foliation. So basically, this is geometric quantization of geodesic flow using polarization, using unstable foliation as a polarization. Actually, I don't know much about this geometric quantization, so I cannot say much more than this, but it's okay, I stop. Any comments, questions?
There's one thing I didn't understand
Yes.
about the commutative diagram.
This,
I suppose to mention something about cancellation.
yes.
But in variable negative curvature, you prove that they are cancellation? No.
I don't know whether there is indeed cancellation, but yeah.
I might have.
But I expect.
And you expect?
Yeah, because this is a big space, and for example, okay, if it is true, the cohomological spaces vanish. So basically, we don't observe the eigenvalues here. just we observe the eigenvalues in this space level.
Do you think that for the zeta function you will only see the spectrum of S0?
Yeah, basically. It's strange, but okay. This is given by that homological structure.
K equals D, the transfer operator really looks like the one for K equals 0. There is only a multiplicative weight to the multiplier by multiplicative weight, so Y should be the transfer operator from K equals D become back from that of K equals D.
Actually, I don't. Okay, let us discuss.
So, any further questions or comments? If not, let's thank the speaker again. And we return in 5 minutes. But
When you go to the next ancient theory, you present a spectrum or you just explore much better?
mas eu queria fazer exatamente. Não seguir o que faz seria bom atualizar o que você já escreveu, submeter o que você pretende fazer. Aí a gente fica. Dá para ir rápido. Dizer o importante.
In this case, you are saying that everybody's
So the eigenvalue itself is
it's possible to make the estimate the maximum
Fernando. Sim.
no. Yeah, maybe in the optical something, but yeah. Maybe we are in the imaginary.
The last question. It is possible to get essential similarity kind of or just hold?
So what we can prove is that eigenvalue is finite and it is conformed to that 0 is 4. So yeah. So we don't see.
I'm asking this because I'm working with this confusing model of transfer operator. And there is an essential similarity when we have the transition. So I wonder if you can push this analysis toward the point where you have this transition. Okay, just one. I have no idea. Thanks a lot.
Quand on fait la transformation de la place, on regarde actuellement, et avec la norme d'opération, on pourrait imaginer que la norme d'opérateur explose en 0, mais ça, c'est pas possible, c'est pas symbolique. Ah, mais ça tombe pas bien. So my question is,
Which
te mostrar um negócio daqui a pouco.
Yeah, is the up the
with the maximal then 3 looks like the operator L0 because there is an editor by missing the weight. So I don't understand why LD should be compact and not L0.
Eles têm um programa de computação na boa, e eles conversam. A semana passada, agora eles não entendem a lagoa pra cá. Isso aqui tá incrível. Desculpa.
So by the way, do you know Maru?
I see. Yes. But we can do that.
Eu acredito em creme e em duende.
So, derivative operator is with a zero. Take quotient on the image.
So donc on essaie de monter sur le bateau. Des full boat space à construire.
So we have lambda k for each level, and we take because the panel of
Eu por acaso gostei dele para mim. Já tá aqui. Beleza. Aí agora você viu com a joystick pra gente conseguir colocar pra cima, é isso?
É isso, ela não. Eu tenho que ver. Ela não falou nada comigo ainda. Tem que ver com ela. Ela vai chegar no próximo horário, ela vai chegar.
Ah, tá. Porque ela tinha me dito que havia uma pra colocar esse pedestal assim, que as pessoas passam na frente.
Sim. É isso. Ela tá satisfeita até, na verdade. Só que ela não tá aqui.
Ah, tá.
Ela foi fazer a matrícula dela agora. Aí vai
Então
demorar.
ela aparece por gentileza, você.
Eu aviso, certo?
next speaker will be Dominic Pietze.
Very good.
Very good. That we will talk about the entropy of non-uniform hydrophilic.
Thank you very much. I hope that everybody can hear me without a microphone. Yes, no? I assume that yes. So, you had your chance to protest. First, let me tell you one thing. I haven't had many occasions to speak to Wellington, but maybe to show how important he is, let me tell you about my first encounter with him indirectly, which was when I took a course on the qualitative theory and differential equations. And then on the list of the lectures, there was a very nice book by Jacob and Wellington on the geometric theory of dynamical systems. And then I was happy to find that it is in Krakow in our library, and a little bit disappointed that the only available copy was a Russian translation. But lucky for me, I'm old enough to be taught a a little bit Russian at the primary school, and because of that book, I also renewed my knowledge of Cyrillic alphabet, and for me it's a big honor to speak at the conference, which is devoted to somebody who I first met through this book, and treated as like a big figure, because only big figures publish books. And okay, let's go back to mathematics. So let me introduce some notation. So there will be two acronyms repeatedly occurring in this talk. One is GIKN, which is an acronym for the authors Gordetsky, Ilyashenko, Klepsin, and Nasky, and the other is BBD for Gyro, Christian, and Lorenzo. And what I'm going to tell you about is a joint work with Marta Łącka and another project with Lorenzo and Christian. And then in order to prove that this lecture is prepared, because I will be using just whiteboard, and later Pablo may say that this is not prepared. So let me tell you an outline what I'm going to do. So first thing is that I will try to present you with the problem, and I will use a lot of nomenclature like Lyapunov exponents, hoping that everybody know what Lyapunov exponents are. But if you don't know, then don't worry, because if I do not define something, it means that later I will not use it. I will just use those terms as a motivation for the problem. Okay? So the first part will be the introduction, telling you the motivation for what we are doing, and later we will make an abstraction of this problem to terms more in terms of topological dynamics and ergodic theory, when we will not need all this extra nomenclature. And then I will try to convince you that we have solutions, and describe how you can get those solutions. And if time permits, at the very end, I will talk a little bit maybe about the proofs. But usually, we shall see. We shall see. And well, don't hesitate to ask me or to interrupt me at any time. So,
Can we interrupt you?
yes, yes, you can. Yes, you can. Yes, you can. So, since the work of Smale and Abraham and Newhouse, we know that uniform hyperbolicity is not as common as we would like to see it. And
Life would be boring.
sorry?
Life would be boring.
Yes, life would be boring. Lucky for us, it is not. And then people were thinking about various ways of bypassing this problem. And one of them was introduced by Pessin, who introduced the notion of the hyperbolic measure. A hyperbolic measure has all the Lyapunov exponents non-zero. And then there's a very naive question. First very naive question is, okay, assume that I have a diffeomorphism on a manifold, which is not a uniformly hyperbolic diffeomorphism. Does it mean that it has a non-hyperbolic measure? So does lack of the geometric uniform hyperbolicity means that you will find the ergodic invariant measure with the zero Lyapunov exponent? And this question is quite, well, maybe naive, but by reasons like Vivien Baladi, Christian Bonatti and Schmidt, or Kao Lusato and Isabel Rios, we know that they are non-uniformly, systems which are not uniformly hyperbolic, and who have only measures which are hyperbolic. And I'm sorry for this terrible nomenclature, which is like non-uniformly hyperbolic systems or not uniformly hyperbolic systems. It can be a bit misleading. So later, Gorodetsky, Ilyashenko, Plepsin, and Nansky, they raise a question, which is to what extent actually the lack of the uniform hyperbolicity can be found manifest itself among the invariant measures for the system. And they, for example, conjecture that there is an open set of diffeomorphisms of the free torus such that each diffeomorphism in the set is not uniformly hyperbolic and has an ergodic measure with zero Lyapunov exponent. And this conjecture was later confirmed by Kleptin and Nansky.
You mean proved?
Sorry?
When you say confirmed, you mean proved?
Proof, yes, confirmed, so... okay, so... yes, and then, well, this spurred a lot of research, and, well, there's a very nice paper for the ICM proceedings written by Lorenzo, and you can write a lot, when you can find a lot of details and historical data I will omit here. And then it turns out that this business of finding ergodic invariant measures with zero Lyapunov exponents follows actually two main approaches. One is an approach initiated by the work of Gorodetsky, Ilyashenko, Kleptin, and Nansky, and the second is the idea following the construction of Bocchi, Bonatti, and Diaz. And all those constructions aim to find an ergodic measure which has zero Lyapunov exponent. But then, of course, once you find an ergodic measure with zero Lyapunov exponent, you would like to know some other properties of this measure. It would be good to, I don't know, classify those measures, to ask questions whether they are mixing or Bernoulli, or do they have some other ergodic properties. And of course, it would be nice to know what is the entropy. And let me now tell you a few words about those two constructions. So, the first construction by Gorodetsky, Ilyashenko, Kleptin, and Nansky goes as follows. We find our measure as a limit, weak star limit of the periodic measures, so measures supported by ergodic measures supported by periodic orbits. So what we do to find such a measure, we start with one periodic orbit, and then, well, of course not. Thank you. And then we find another orbit with a much larger period, but this orbit should have the property that I will now draw the orbit like a continuous line, but it is a discrete orbit with many points inside of it. So this orbit should behave like this, that it follows closely the previous orbit for many iterates. The whole orbit goes around the other very close for many iterates. And maybe at the end, before we close finally our orbit, we do some excursion somewhere in the space.
What do you mean there? I mean, it's essentially going point by point?
Point by point. So
here.
I have two orbits. One I can call gamma, the other I can call lambda, and I have a delta, a subset of lambda, which has a large cardinality compared with the cardinality. So this is like epsilon, and epsilon is close to 1, right?
The blue line is misleading, so to speak. You stay close to the 3 points. You never go until you begin to escape. You don't go. You stay in close to one of the 3 points.
Okay, so let me write in symbols for those who don't like pictures. Okay, so I have two subsets. I have two periodic orbits, gamma and lambda, and I have a big subset delta of lambda, and then I have a function from delta to gamma such that I have the following condition. that for each point x in delta, the distance between t j x and t j psi of x is small for the whole orbit, sorry, it should be here, gamma. So I have many points here, such that with the point in the delta, I can pair it with a point of gamma, and then those 2 points will go together along one cycle of gamma. And then the red point can go somewhere else, but then I will find on the same orbit of this point another red point, maybe here, which will go around gamma for the whole orbit of gamma. So if I reduce gamma to just 1 point, I can see another orbit such that most of the point of this another orbit, the set delta will be close to this black point, but there might be some points outside small neighborhood of the black point. So this is this kind of behavior. And then I built next orbit approximating blue one. So then I will take, if I had more colors, I could go a green orbit going around blue one, staying close to blue one many times, and then making an excursion, etc. And now, if I have I have 2 parameters. One I called epsilon, the other I can call delta. And if I have a sequence of orbits such that the product of epsilons n, so those epsilons at the step n, is going to 1 fast enough to see that that product converges, and deltas are going to 0 fast enough to make my sum to be converted, then Gorodetzky-Lyoshenko-Klevtsin and Nasty proved that the sequence of periodic orbits going close next to each other according to the scheme has a weak star limit, which is not a big deal because weak star topology is a compact topology, but what they needed really is they needed to prove that the limit is an ergodic measure, and usually it is not true that the limit of ergodic measures in the weak star topology is ergodic. So all this construction is meant to make sure that the limit is an ergodic measure. Limit is an ergodic measure, and then the limit will be supported usually on something uncountable. If you really grow the periods, then you will see that the limit is supported on something uncountable. And then you can also, well, if you visit the regions when you have like the contraction in the central direction and expansion in the central direction more or less equally, you can also distribute these constructions and expansions along the orbit so that in the limit you will see something with the zero Lyapunov exponent. But we don't need that for the rest of the talk, so I just mentioned that there's another part of the Gorodetzky-Lyoshenko-Klevtsin and Nasty construction which I omit because it is only meant to get the zero Lyapunov exponent, but the scheme for obtaining a measure is essentially that. There are also additional conditions. And so what we know about this measure, we know that it's ergodic, but what is the entropy of that measure? And to my best knowledge, it was not known, the question was asked during a mini course and Olmue during the non-uniformly hyperbolic conference by Lorenzo. I was there and with Catherine and with Francois, we discussed a little bit after Lorenzo's lecture, and then Francois gave me one code word which is f bar, which it turns out is sufficient to solve the problem, because what we now know, I can state the theorem, and this theorem is actually a corollary of a little bit bigger theory, and this is by Marta and myself. And this theorem says that every measure obtained by this construction by Gorgetsky, Lashenko, Klepsen, and Nalski.
Che sei GYKN?
For me it's GIKN construction is loosely Kronecker. I will explain in a second. And this fact of being loosely Kronecker implies that it has zero entropy. So, what is loosely Kronecker is that we actually obtain a little bit stronger result than just answering the question about the entropy, because we actually classified all those measures with respect to so-called Kakutani equivalence. So in the ergodic theory we have a natural notion of isomorphism. This notion is well known, but there is also a weaker notion of a Kakutani equivalence, which is more or less orbit equivalence for the measure preserving systems. And we were able to show that each measure constructed by GIKN is in the class of equivalence of ergodic rotation of compact groups. What does it mean? It means that you can think about each measure as a measure obtained by the following. You take the circle, you take any irrational number alpha, and you take the rotation by alpha, and then you take a set, Borel measurable set with positive measure on the circle, and you can imagine that you are taking an induced system onto this set. And
into the red set.
And into the red set, yes. So we are taking the Poincare return map, and this gives us the induced system, etc. And then the statement loosely Kronecker means that for each measure constructed like that, I can find a Borel set here with positive measures, such that the induced system and this system will be isomorphic.
Usually you induce something which is invariant under some iterate or something. So the red part turns. So
no, there are which part turns?
The red part is turning.
No, the red part is fixed. It's a subset of a circle. So and then I take a points which return to the red part, and then that's a system, because almost every point returns. Mm-hmm. And then this gives me, up to measure 0, a well-defined transformation from the red part to the red part. So we can find for each system like this, we can find a red part.
Red part is some interval or something?
No. It is. If we really take interval like this, we will only obtain these systems which are isomorphic with the basic irrational rotation. But here we will get much more in the sense. And then it's really not important that that's the circle. We can take an odometer. Any compact group is as good as the other. And
but you need a translation of that.
We need an ergodic group translation. Yes. But so this result classifies all those measures up to the Kakutani equivalence, and well, okay, we have a conjecture that maybe here we can get that all those systems are rank 1. Unfortunately, to define rank 1 system, Sebastian Ferenczi wrote a paper in which a section with the definition of rank 1 system is entitled "A Nightmare for a Lecturer." So I'm not going to define what the rank 1 system is. It is a nightmare.
So what? You can still have slow entropy.
Sorry?
You know if you have slow entropy for that?
No, for that systems you know that you have to have zero entropy.
No, but slow entropy.
Oh yeah, we can. No, but probably we can. This we don't know. It would require a much deeper insight into the parameters of that construction. Okay, and then let me go quickly to the second construction, BBD. And this construction goes as follows. You imagine that, of course, your space is a manifold, but in the actual construction. But the abstraction needed to consider the entropy is that you may think that you have a continuous transformation from a compact space to itself, and that's our space. And you imagine the following, that in your space you have two compact disjoint subsets, K0 and K1. And then you imagine that you have a point, and what you know about this point is that you have a subset of times, so subset of the positive integers, such that you can do the following. For every function from I to 0, 1, there exists a point x such that at times in I you know the position of x with respect to those two sets. So you have a knowledge about the
Ti of x. You wrote Ti of x.
Ti of x, yes. So you have like a stroboscopical knowledge about your orbit. You cannot say that it always. You cannot say where it is every time, but along some sequence of times, you know that it follows a prescribed itinerary with respect to those two closed sets. And then, of course, to find such points, you use all those flip-flops and blenders and stuff like that. With, I'm afraid to tell you in front of Florence, so it's better not to touch this subject. But the abstraction is like that. Yes, that's more or less the essence of the stuff, and then using some extra knowledge about where are those sets and what has happened, both Fibonacci and Diaz were able to say the following, that for every measure generated by this kind of point, so if you choose your function psi properly, and if you choose the right sets and etc., then you have a statement like this, that for almost every measure, so let me remind you that the set V of x is a set of measures generated by a point. So in order to think about measure generated by a point, we denote by delta the Dirac measure concentrated at the point, and we take the Dirac measures, we take the first endpoints on the orbit, and then we take the uniform measure on these endpoints. That's an empirical measure on the first segment, end segment of the orbit. That's a probability measure. So the sequence of probability measures has this points, limit points, and every limit point of such a sequence is an invariant measure for the original transformation. So we may speak about set of invariant measures generated by a point. And then with some extra technical assumptions, you can prove that, okay, if you take a measure generated by a specially constructed point, which is called controlled point in the BBD papers, then this measure has an ergodic decomposition, and for almost every measure in this ergodic decomposition, you can claim that this measure is ergodic, has positive entropy. No, it is ergodic, has full support, and it is non-hyperbolic, so it has zero Laplace exponent. But again, in this original construction, it was the question whether you can add to all those conditions that the measure has positive entropy. Because in the other version of the construction, when you force your point to stay in K0 and K1 always, you clearly have a factor map onto a shift space, and then you have a measure with positive entropy, but you lose the full support because you are only supported on the subset of the space. Okay? If you force for every time and in and 0 that your point is either in K0 or K1.
Another method for period doubling, for instance, would be like that, and it has a entropy.
Yes, but if you choose the right function psi, for example, if you choose a generic point for the Bernoulli measure, then you will see the full shift as a factor for that order. So it's you don't even need to take generic point. You can just take the sequence of zeros and ones, which is dense in the space of all 0 and 1 sequences. So it's, you can work on that. So, and then again the question was whether you can now produce a positive entropy in this kind of the construction, and this is the answer is again yes. So let me formulate the theorem.
When you say again yes, because before you said no.
No, again yes, in the sense that again we confirmed the conjecture. Okay. Theorem, and this is. This is like the corollary of our work, that for every n greater or equal than 3, there are n-dimensional manifold M, U an open subset of the space of C1 diffeomorphism of M, and there exists a constant C greater than 0, such that for every F in U, has an ergodic, non-hyperbolic, fully supported invariant measure mu with a uniform bound on the entropy. So it's bigger than C. So what is a novelty? What is the difference between this result and the results previously obtained by Boki, Bonatti, and Diaz? Is that we obtained a robust result, so we have an open set when it is a subset of robustly transitive diffeomorphisms, and all measures are fully supported, ergodic, non-hyperbolic, and they all have the entropy bounded below from 0. But, like I think from the result of Ali and Jagan Yang, those entropies are bounded below from 0, but they are also usually bounded above, uniformly bounded from the topological entropy. That's interesting. It's a nice. It's a nice. Okay. So now, what is the method of obtaining such result? It's actually again an abstract result in topological dynamics and ergodic theories. It is like assume that we have T from X to X continuous. X is a compact metric space, and we K0, K1 are disjoint. So and we have this condition. Then for every function I, we have this. And now, if psi is equal to y restricted to I for some y, which is a sequence of 0 and 1s, generic for like P1 minus P Bernoulli measure, with P greater than 0. So it means that psi is a function from I, so I look at the coordinates of y in I, and then I put accordingly the value of psi here. And I is a completely, we need some deterministic sequence. I will explain in a moment. With the upper density positive, then every measure generated by a point X which follows psi according to the scheme has entropy bigger or equal than here. I'm sorry, I should put the lower density. Okay, the lower density of I times log 2. That's the abstract statement which, joined with the machinery introduced by Bocchi, Bonatti, and Diaz, gives this statement, and also some more, but there is not much time to talk about it. Okay. So we can take one half, right? No. I just thinking that's a Bernoulli measure which independently gives probability P to 0 and y minus P to 1. Oh, of course. Thank you very much. It's always good to know that people are not sleeping. So that's the Shannon entropy of P1 minus P, right? That's the. Thank you very much, Hansel. Okay, so now time permits to tell you a few words about rules, because that ends the part with the introduction to those to the results. So I described more or less what is happening. So yeah, completely deterministic. What is the completely deterministic set? So if you have a set in N0, you can consider its characteristic function as a point in the shift space. And now, because this point in the that's a point in the shift space, so shift space is a dynamical system, so you can now consider the set of all measures generated by this point with respect to the shift point. And completely deterministic, that's a notion introduced by Tetsuro Kamae and Benji Weiss, means that for every measure generated by this sequence, the Kolmogorov-Sinai entropy of this measure is 0. It doesn't mean that necessarily we need to have topological entropy on the closure of its orbit to be 0. It just means that along this, looking at from the 0 position, looking at the measures generated by this point, we only get 0 entropy measures. This proof is an well, uses only very basic ergodic theory, but there's one non-trivial result a bit inside, which is which uses an observation by Kamae and Weiss. And this is a very nice observation and interesting fact, meaning that if you take this sequence, which is generic for the Bernoulli measure, in other words, if you take any binary expansion for a normal number, then if you look at the subsequence along positions in the set I, which is completely deterministic, then you always obtain again a generic point for the Bernoulli measure or a normal number.
Yeah, but you cannot find it.
Sorry?
Tell me one normal number.
No, we can't. So there's like Turing's construction of algorithmic construction of normal numbers. So it can be even given nice construction. So, but here it is easy to see that load of large numbers imply that for almost every normal number we will get such a procedure. But here the statement is much stronger. For every subsequence along a completely deterministic sequence, we obtain again a normal number. And this is required.
Can you use that to construct some?
Well,
if
I want, yes. If I want, yes. But of course, in order to construct some, and if you want to keep the notion of constructibility somehow meaningful, you also have to have the constructable I, which is possible to do, but yes. Okay. So this is enough about this proof. About this theorem, we actually needed to introduce. Paulo, I have like 10 minutes, right? Okay. So for this theorem, we needed to introduce a new notion of convergence for invariant measures, which is like a byproduct of the Francois remark that it looks like an F-bar. This construction, so we are now going back to the construction of Gorodetsky, Ilyashenko, Klebs, and Kowalski. And now the point is that we want to see this construction as a construction of a convergent sequence, but in a new metric, or new pseudometric in fact. And the pseudometric is like a topological version of something which was known in ergodic theory since the works of Feldman and Katok. So let me, given 2 points, so we consider now 2 points. X, x0, x1, x2, etc. and y, y0, y1, y2. So those are two sequences. You can think about this as sequences of zeros and ones. And then you define what's f bar n of x and y. It's equal to 1 minus maximum k such that over n, and let me write what is such that k such that there exists one bigger or equal a1 bigger. Okay, so there exist two subsequences from of the elements from, okay, so it should be 0 here, 0 here, here 1 and minus 1 and minus 1. Two subsequences such that if I look at points x a1, x a2, x ak is the same as y a j1, y j2, y jk. So I have two words. And then I'm trying to find a common subwords by deleting some entries. But those I can delete, like here I can delete this one, and here I can delete this one, and I will be close. So a good example is to consider two sequences, 1 0 1 0 1 0 1 0 1 and 1 1 0 1 0 1 0 1 0. So those two sequences differ at each position, but if only I remove like the leading entry here and the last entry here, I see the same sequence. So the f bar distance is small. This fn bar distance is small, as if n goes to infinity, then it is clear that it goes to 0.
That's the only type of comparison you make, or anything which is
Sorry?
fine? It's only the first one and the last one, or you can do it?
No, I can, in the definition I can do the same, but in the example it is enough to take the first one and the last. Take down. So, okay, the question is whether you can define a similar stuff, and then you take the f bar distance between x and y, you just take the lim superior upper limit of fn xy. So this notion was known for Feldman and Katok. It's surprisingly not well described in the literature, but you can believe that those guys knew a lot about it, but they never cared to write it down. But now the question is, okay, can you do it for topological system? Okay? And then the idea is again the same. In the topological space, you consider two sequences. One is the orbit of a point x. The second is the orbit of a point y. And now you are looking for the increasing bijections, which are not necessarily defined on the whole natural numbers, but just on the subset, such that the red line means that those 2 points are closed, delta close. And then you try to do two things. Then you want to make delta as small as possible, but the density of red lines as big as possible. And that's a little bit like in the definition of the entropy. You make it in stages, so you define what's Fn with a subscript delta, then you go with the limit superior with delta, and then you take the infimum of all deltas when it holds. The formulas are maybe not that important, like the idea of having that. And then the next step is you want to translate this pseudometric to the convergence of measures. And then to do that, you are not allowed to use orbits, because not every measure has a generic font. So then if you want to do it, you run into the troubles. But you can use an older observation by Zygmunt, which says that every measure has a quasi-generic sequence. What's a quasi-orbit? What's a quasi-orbit? Quasi-orbit is a sequence.
Can you repeat the statement?
Okay, I can repeat the statement. So, for every measure, invariant measure, ergodic or not, there exists a quasi-orbit, generic for me, mu. And what's a quasi-orbit? Quasi-orbit is a sequence of points in X, but built from the longer segments of orbits. So you may have a situation like that you go with 4 points from one orbit, 8 points from another orbit, 16 points from yet another orbit. But if you look at the measure generated according to the same formula as here, as a limit of this uniform points, you will find your invariant measure in the very end. So those are like pseudo orbits in some weak sense. And then you may say that a sequence of measures converge in the sense of we call it Feldman-Katov pseudometry. And it should be said that the sequence of measures converge in the Feldman-Katov sense on the abstract compact matrix space if you can find a sequence of those generic points, generic quasi-orbits for those measures in the sequence which form a convergence sequence in this Feldman-Katov pseudometry. And this introduces a new notion of convergence. And it turns out that this notion of convergence has a very nice properties. So I will just tell you what those properties are. So the entropy function is lower semi-continuous with respect to that convergence. Entropy measures are close subset with this sequence. This pseudometric on the space of measures is complete in the sense that if you can find a Cauchy sequence of generic sequences, then you are sure that you are converging. And finally, all this fits to the GA-Cayenne construction. So exactly what they construct is the Cauchy sequence of measures in this Feldman-Katov pseudometry. And now we can provide like an abstract proof that the limit is ergodic because all those sequences are generic for the ergodic measures which are periodic orbits. So the limit has to be ergodic. The limit has to have entropy 0 because lower semi-continuity is okay for us because we have a sequence of 0 entropy measures. So the entropy of the limit measure can be always smaller, but it must be 0. And this Kakutani equivalences classes are closed, at least for the loosely Kronecker case, with respect to this convergence. So we got all those results, and we hope that the limit of the periodic measures are really rank 1 in this trigonometry, but they couldn't find the proof yet. Okay, my time is over. Thank you very much for your attention.
More questions or comments?
Sorry? Well, here constancy once it you need to take logarithm of 2 times the set when you have control times the lower density of the set when you have control plus the flip-flop construction requires you to take some usually large k in order to have this control. So unfortunately this constant, this you can make quite large, but this k you have little control and this kills it all usually to a very small number. So it's we would like to know more about it, but I'm afraid it's because this k kills it to 0. Yeah, it can be it can be found theoretically at least, right? It depends on the parameters you use, but there are so many of them. So let me write. So
just the idea.
okay, the idea is that you have your two sequences. Those are orbits. Think about orbits. And now you want to find moments when you can find pairs of points on one orbit, the second on the second orbit, which are close. So assume that I'm drawing a red line if 2 points joined by this red line are closer than delta. So you want to find a pairing. You consider all possible ways of making those functions, and you want to find the one which has the densest density of red lines. So you skip as few points as possible, and you want to take delta as small as possible. So you always get something smaller or equal than 1, but the point is that you want to find, and then you need to somehow make the infimum of the deltas such that you find the bigger than 1 minus delta.
And you need a good density of the...
Sorry?
You need a positive density.
Yes, you need a positive density. So you need as close density to 1. So this means that for given delta you can find a set with density bigger than 1 minus delta. But you cannot exchange all distance. You have two parameters, and you try to optimize between those two. Density and distance. And you want to somehow find the optimal one. So this is hidden here, that you are taking the infimum of those delta when you...
Sorry. And to get this, you have to define the other cylinders in the space of...
Yes, but then I just defined, I said the delta and pairing of the two sequences is a function phi which has a domain contained with 0, 1, n minus 1, and it has a range contained in the same set, such that for each pair of the in domain and in the range, the distance is smaller than that.
So I have one question. Do you expect to build examples where C can be taken as large as topological entropy, or
no? It's Ali can forbid that.
Just conjecture.
So forbid or conjecture?
Some context it is proved.
Oh, okay.
So in some cases it is for sure not true.
Yeah, I assume
that
was
is
my
the,
guess.
so in general, you don't know. Almost surely, probably there are examples where it is true, but it's always the question is how often it is. But.
So let's try to speak again.